So this is what we had, right? And then we said that we want to use a Taylor series, as you can see, coefficient. So 그래서 테일러 시리즈를 사용한 differential equation approximation은요, 그냥 진짜 노가다예요. 그죠? 왜냐면 initial condition 있으니까 y의 at the center는 걱정 안 하셔도 돼요. f of 0 or f of a, you don't have to worry about it. But the ones that you gotta worry about are the coefficient of a polynomial, such as the f prime of a, f double prime of a triple prime of a, etc., etc. However, that's okay because your differential equation is technically gives you dy over dx. And what you have to do is just keep differentiating using the implicit differentiation and product rule. 그죠? We just keep doing it. Second derivative, third derivative, and it's left as we already did it. So if we put that in, we got that, right? On that approximated polynomial, we're gonna put x to be 1.1, should give you the approximately 0.1107. Okay? So again, this is a who? Approximation. Okay? This is again who? Approximation. So let us have a look at this fancy function. So let's have a look. Try to build up the Taylor series of that function at the center of who they say? Negative pi. Remember, if it's something of a trigonometric function, your center is very likely to be in terms of pi rather than integer. Understood? So let us try to solve that together. But let me take a seat. Hold on. Okay. Let's get started. Page number 107. I'm on it. 그래서 뭐가 되게 중요해요? Yes, not only noticing the differential equation, but also noticing your initial condition is given to be who? Negative pi, comma, pi over 2. That, my friend, is your initial condition. Understood? I'm very happy with this. I'm happy with this. So as you know, I'm gonna use our formula of the Taylor series of what you already have learned in great details in the last chapter, right? And they asked me to approximate up to degree 3, so maybe I will differentiate this 3 times. So that's what we have at this moment. Understood? Okay, so for him, it's a negative pi, comma pi over 2. Okay, so let's try to solve it. So if it's a f of negative pi, it is pi over 2, right? It's given those initial conditions x and y. Understood? So you can already put pi over 2 there. But and also for the first derivative, right? Your center was given to be negative pi, so you can use the initial condition for your differential equation, which technically gives you the first derivative. So if I then plug the negative pi, comma pi over 2 on him, cosine negative pi is the same as who? Come again? Cosine negative pi is in fact negative 1, right? So it's going to be negative 1 minus sine pi over 2 is 1 and plus pi square. So in fact, your first derivative is a pi square minus 2 at the center of negative pi, comma pi over 2. Okay, let's go to the second derivative, which is going to be then given as what? Then I need to differentiate this twice, right? I gotta do the implicit, right? So if I do the implicit, if you differentiate cosine, what do you get? You're gonna get the negative sine x minus cosine y times who? dy over dx plus 2x is what I have, right? And then I'm gonna put negative pi, comma pi over 2 into my second derivative as well. If you did, sine pi is 0, cosine pi over 2 is also 0, So I'm only left with just evaluating the 2x and x equal to negative pi. If you did, it's going to be negative 2 pi. Okay? But I need the third derivative as well for the degree of 3, so I'm going to differentiate once more. D cubic y over dx cubic. That means you're going to differentiate the second derivative with respect to x. So if you differentiate the sine x becomes cosine, so negative cosine x. And as you can see, I got to do the product rule on the cosine y times dy over dx. If I did, it's going to be by the product rule and implicit negative sine y times dy over dx squared plus cosine y times d square y over dx squared. So, but then, you know, we're subtracting with him. So it's going to be changing the sign, plus and minus. That's what we have. Plus 2x, if you differentiate 2x, what do you get? You just get 2. Right? So that's what we have. And I want to evaluate at the x equal to negative pi and pi over 2. Then let us try to evaluate those points. So if I put the pi on cosine, it's negative 1, but it's negative cosine, hence it becomes 1, right? And sine pi over 2 is, what is it? 1. And then dy over dx was pi square over 2. Sorry, pi square minus 2, right? But I need to square that, you see? That's what you're going to have. Minus cosine pi over 2 is 0. So I don't have to worry about him, right? So it's going to be just simply 2. Right? We need to add by 2, right? So, yes. Good, good. So, you know, your third derivative is given as a pi squared minus 2 squared plus 2. Okay, okay. That means check if I've done it correctly. Yes, I've done it correctly. Okay? So, but we are not done because we need to plug those in for my Taylor series. So again, my first derivative was who? At the center, and initial condition was a pi squared minus 2. So I will use it over 1 factorial times x. And then what was your a? Negative pi, wasn't it? So minus a will be plus pi. That's good. And your second derivative was who? Negative 2 pi. You see? So I will use it. Negative 2 pi over 2 x plus pi squared. And your third derivative was who? Was this coefficient, right? And this guy divided by who? 3 factorial times x minus plus pi cubic is the Maclaurin series that we need to do. Understood? Good, you know, dividing by 1 factorial is the same, so I will just put it here. And dividing by 2 is a 2 over 2, so that cancels out. Okay, so that's what I have. And that, my friend, is going to be there for my function approximated using the Taylor series. Okay? Then you can put whatever value you want in terms of x. Maybe it's going to be the x value that is close to pi, right? So if you did the pi, maybe something like the 6분의 7 pi, right? You can evaluate now 7 pi over 6 on him because simply it's close enough to my center. So the cubic polynomial of a Taylor series will approximate it very well. Okie dokie? Good. So far, so good. That completes all the differentiation.